All right. We're going to be in the week 14 folder, and you're going to start with compasses and Earth's magnetic poles Nearpod notes. Should look something like this. So if you see that, you're in the right place. All right. So we're going to start off with a video about the magnetosphere. The magnetosphere we talked about yesterday, and we talked about what its usefulness is, and how it is single-handedly keeping us alive, and most people don't even know about it. There's going to be one question that pops up when we start. All right, so would we be alive without the magnetosphere? You're good. So thank God for the magnetosphere. It's like an invisible shield that protects our second invisible shield, which is our atmosphere. Our atmosphere is very important to us as humans. It keeps everything we need in and alive. So there's a lot going on out there that we don't even think about on a daily basis that keeps us alive. All right, good work. All right, so we're going to start with a compass today. So we've been talking about how the Earth has magnetic pull, and even though like if you have like a paper clip on the desk or your refrigerator is magnetic, it's not like flying across the room anywhere. It's enough of a pull to notice. So if you balance basically what happens with a compass is you balance a small piece of metal on a needle. The piece of iron metal on the needle is attracted to the Earth's magnetic pull enough to change where it goes. So it'll always point to the magnetic poles of the Earth. Now the magnetic field points towards the magnetic poles. So if you take a small magnetic needle, it'll spin inside of a compass. That's why like you can shake it around and it'll move. If you ever use a compass like one on the picture, and it'll point towards north. This is good for navigation, especially when you don't know where things are. So if you used one in like where you are in Cincinnati, like we normally divide up our neighborhoods in like north, south, east, or west, and central. I've noticed too. So like for example, if you live like downtown, like near downtown, that's kind of south. I live on the west side of town, so I live west. East side of town would be like way out there by like Milford, Anderson, Turpin. Those schools out there, those are to the east. And then north would be like Blue Ash, Mason, those areas, or towards Columbus even. That's north. So like if I was like dropped somewhere randomly in the middle of Cincinnati and I had a compass, I could navigate west to try to find my home because I know I'm in the west direction. Um, so that would help. So that's how this works. It orients you. You can orient yourself based on where you are to try to find other places. I really wish we were in school because we normally do like something where we walk around school using compasses. So it always points north. You don't have to travel in the north direction, but as long as you kind of keep the compass facing that direction, um, whatever area you point the compass in, it'll point to where you're going. Now keep in mind, all the compass is a magnetic needle. So it's drawing off the small pull of the magnet in the earth, which is all based on the that molten iron and rock that's underneath the earth. All right. So if you need more time, raise your hand in the chat. Click the raise hand button. Is this one? All right, going once, going twice, sold. All right. So think about this. Since a compass is just a small magnetic needle, what would be a way to throw off your compass reading? So this is like, what's one thing that would make a compass reading inaccurate? Give me like more than like one word answers, please. It's okay if you're wrong too. Like I'm not grading this if you're right or not. I'm seeing like where your brain's at. So don't worry about if you're right or wrong. Take a random guess. Okay. Good guess, Jaden. Come on, guys. This works. So, like, honestly, if you just sit there, this class can be boring as heck. You need to like participate. Give me something. Jason, give me something besides water. Compasses work underwater. Guys, this is part of your grade. Come on. Give me something. What is something that could cause a magnetic needle to be thrown off? What is something that could cause a compass to be thrown off? All right, thank you, Jason. That's a good answer. Watch the video. Watch the video in the question. Sorry, I had something in my throat. Andre, JJ, Eric, come on. You don't have to be right, just guess. It's okay. All right, good job, Eric. Oh my guys, like this class goes so much better when you guys participate. All right, good. All right, so look, if you use a magnet, like I said, the needle in a compass is magnetic. So if you get a compass near a magnet, it's gonna screw it all up. So in the beginning of this video, you can see the compass is pointing north. And then as you get a magnet near it, it screws it all up. So most of the time in the United States or in the world, the compass works normally. You don't get close enough to a magnetic field that it would screw anything up. It would screw a compass up at all. But know that these things aren't perfect. They are just basic general ways we can find our way around. Because there are places on Earth where compasses don't work. So like, for example, this is a place in Africa where in the Republic of Congo, where for some reason the compasses just spin. They don't work. So this could be, they call it an anomaly. An anomaly is just a place where normal rules don't apply. So it's kind of like an outlier, something that's not normal. So right here is, for some reason, compasses don't work. Okay, there could be sitting on a large bed of iron there, large iron deposits that mess up the immediate magnetic field there. But this also doesn't work. There's also a place in Mexico where radios, magnets, and like all like electronic things just plain don't work for some reason. And they call them anomalies because they can't really figure out why it's happening. Pretty cool stuff. All right. Good. So the reason how this works is that an Earth has magnetic poles. Earth's iron core creates a magnetic pole on Earth. All right. So there are two poles that share kind of the same location, and this may be a little confusing. All right, because there's a magnetic pole, and that's where the magnet is attracted to. And then there's the geographic pole, okay? So the magnetic pole is where your magnet is attracted to. So if you point a magnet, if you have a compass, where it's pointing north to the magnetic pole, that's what it's pointing towards, which is basically the same thing as geographic north. So like geographic north would be if Earth was perfectly up and down. You guys should all know or have heard somewhere that Earth rotates on a slight tilt. But the geographic North Pole is like the tippy top of the Earth. The geographic North Pole is what you think of when someone says the North Pole, like Santa's workshop, is at the geographic North Pole. The magnetic North Pole is something completely different. It's where your magnet or your compass is attracted to, which may be a little different than the geographic North Pole. It's about these two things are about 600 miles apart. All right. Now that's a long distance if you were going to walk from one to the other. However, when you're down on Earth and we're down like in the United States, If you draw that line out, it really doesn't make much of a difference. So it'll still basically get you where you need to go, even though these poles are in two different places. So this is something if you think about, it makes sense. So just kind of go through this slowly. The North Pole of a compass points towards the geographic North Pole. However, it's the South Pole of the magnet because on the compass you're physically holding in your hand, remember, opposite poles attract each other. So the North Pole is next to the magnetic South Pole because the poles of your magnet need to be attracted to the opposite. So the needle on your compass that points north is the south pole of a magnet. So the south pole points north and north pole points south. I know it's a little confusing, but if you think about the North Pole, all right, geographic north, that's like up to us, would have to be attracted to the South Pole of a magnet that we use. All right, I'll give you guys a few more seconds to copy this down. Okay. All right, so next up, all right, go to Schoology, complete the exit ticket in the week 14 folder. When you're finished, turn those in, and then turn in your notes as well. If you need to see, if you missed out on any of the notes, if you're looking at my screen and you go to either one of these assignments and click on the link that I attached here, Earth Magnetic Field Slides, it'll take you to a Nearpod that you can control yourself. And you can go through here and see everything. Okay. So if you need the notes yourself, this is how you get them. If you missed anything or came late today, that's how you do it. So make sure you get the exit ticket done. It's 3 questions. Make sure you use your notes. The exit ticket's not like a quiz. It's not. I'm not trying to see what you remember. I'm trying to see how you can apply what we talked about today to it. One of them was one of the questions we did in the Nearpod today about what could cause a magnet to mess up. Okay. And then tomorrow I'm going to try to work on some sort of magnet project for you guys, or where you could use the magnet, the compass on your phone. But I don't know. It's hard. It's hard to hard to definitely do when not in person. All right. Does anyone have any questions? All right. We got a few more minutes till class is over. Make sure you're getting that exit ticket done.